Okay, so we're going to go ahead and take a look at a traverse using the velocity pressure method. Our actual file directory is C. I do have a project right now under Documents and Settings, Air Balance Tools, Commercial, Customer B. We have some files here we can go ahead and view, so I'm going to go ahead and copy this address. I'm going to go ahead and paste it in the directory, entering a slash. And we'll go ahead and save that. So we have our file directory set. Now we're going to go ahead and identify what our file number is going to be. Air handling unit number 1. Okay, so this particular air handler is a 30 by 40 inch air handler. It produces about 12,926 cubic feet of air per minute at 0.15 inches of velocity pressure. Our total average feet per minute is 1,551, and our area is 8.33 square feet. So you can see our X and Y traverse averages. This air handler was labeled supply 1, 8 inches from the roof penetration, and we're going to say at 2 inches of static pressure. I'm going to go ahead and save to XML, save to text. So we take a static pressure. The static pressure is the outward pressure being forced upon the inside of the ductwork in all directions. We have a magnehelic gauge here that goes from 0 to 3 inches. We have the high side of the gauge that goes to the inside of the duct because it's above atmospheric pressure. It's positive. We got the low side to atmosphere, and we're measuring 2 inches. So we have a pickup tube tied to a magnehelic gauge that's 0 to 0.25. We expect the pressure, the velocity pressure coming across the duct to be approximately about 0.15. As we put the pickup tube into the duct, it's directional. Air is flowing down. This is our high side, and it's marked high. And then this is our low side, and it's marked low. So air is coming across this way. There's holes along this tube on both ends. These tubes lead into the magnehelic. We have the magnehelic high side and the magnehelic low side. The difference between these two is going to be the velocity flow across this duct in inches of water. So this will measure in inches of water, this magnehelic, and it's a gauge that goes from 0 to 0.25. Now we can see the pickup tube all the way inside the duct, and we can see our reading. So now if we came up to this air handler, we knew the reading was typically about 0.15 or somewhere in that vicinity. And we came up to the duct and we saw 0.05. We just lost quite a bit of CFM. And this could be due to a number of reasons. Could be broken duct, could be something like a belt slipping or motor speed, could be a variety of things, something blocking the entry of the fan or the inlet of the fan. So now if we take a look at the report, we have all the site information, date, job number, who entered the information, and in this case it's the square duct. We don't have a round duct diameter here, so it's obviously 30 by 40. We have a square duct 30 by 40 inch. Our average velocity, CFM, for our X and Y axis, our total CFM, total velocity pressure, total average feet per minute, our area, and the label, where the reading was taken, and what type of static we had on that duct. Okay, now we've had a good refresher on a couple of calculations related to airflow. We just got a task that we had a 3-story building, and this 3-story building has a major pressure issue, and we have a transmitter that went out on a Paragon air station. It's a 4 to 20 milliamp. It sends a signal to a DDC system, and we're going to have to go out and troubleshoot it. So the first thing we want to do is we're going to go ahead and go to customer C. We got a supplier transmitter. We're going to copy that directory. Okay, so this inlet of this fan, we have our pickup tubes. The diameter of the inlet of the fan is 42 inches. We have a transmitter that's rated, and the only thing that we know is it says it's 88,000 cubic feet of air per minute that this is rated for, this transmitter. We've got a MagnaHelic in its place so we can measure the velocity, and the LCD is not reading that's tied to this transmitter. It's got voltage, and we don't have a 4 to 20 milliamp signal, and so now we got to determine what we're going to be able to do. The customer has another transmitter, but this one's rated at 60,000 CFM at 5.54 inches of water. This was designed originally for a fan with an inlet area that is 6.368, which is equal to about a 34-inch diameter fan, and it's rated at 9,422 feet per minute. How do we do this? Well, the first thing we want to do is let's take a look at this transmitter. Now we know that 4,005 times the square root of the velocity pressure times our area equals our CFM. So we're going to take our velocity pressure, 5.54, the square root, multiply it by 4,005. We get our feet per minute. We times our area, 6.368, and that equals our CFM. So now what we're going to do is we're going to go ahead and get our original reading. So this transmitter is rated at 88,000 CFM. 88,000 CFM. We know the diameter is 42, so we can guarantee that the transmitter is rated at 88,000 CFM at 5.25. Now we have another transmitter that's rated at 5.54. Our diameter doesn't change, but now we have our new range for our transmitter. We have our scaling here for our transmitter. So at 20 milliamps, a 5.54 transmitter, and that means 5.54 inches of water, which is the same as this 9,426 feet. This doesn't change. If our diameter changed, say we went to a 34, our CFM would change, but our feet per minute doesn't change, nor does our inches of water. So these are directly related. So we can use this 5.54 transmitter in a 42 inch inlet of the fan, and we have to rescale our transmitter at our DDC or our controls, whether it's Johnson Controls, Allerton, ALC, Siemens. So it's a 4 to 20 milliamp signal at 20 milliamps. This transmitter in this piece of equipment is going to equal 90,695 CFM. In most cases, there is a calibration or an offset that you can place in the DDC system. Now, if we had a Verus transmitter and it was 5 inches, a Verus transmitter can be scaled for 2, 3, 5, multiple ranges. So if we had a Verus transmitter set up as a 4 to 20 and we had it set at 5 inches and it was a 4-inch diameter, we would have to scale the input that the transmitter is feeding into at 86,161 feet per minute. For this particular device to fit into this application, we're looking at a 90,695 cubic feet per minute as our scaling for our input on our DDC system. Let's take a look at our reports. So in this case, we got a 42-inch diameter, 5.25. This was the original transmitter that was in it. Average velocity, our CFM 88,000, our feet per minute in our area, measured location. We actually measured at the transmitter location. So in this report, this is going to be our new scaling for the 60,000 CFM transmitter that was rated at 5.54 will now be rated at 90,695 for this particular application. And the original transmitter was rated for 34.1614 diameter or 34-inch diameter at 5.54 inches of water at 60,000 CFM at 9,426 feet per minute with an area of 6.36.